In the final decades of the 19th century, physics stood at a strange and uncertain crossroads. Electricity and magnetism were no longer mysterious curiosities demonstrated with sparks and coils in lecture halls. They had become central forces in science and industry. Telegraph lines stretched across continents. Electric lighting began to replace gas lamps. Dynamos hummed in laboratories and power stations. Yet beneath these technological triumphs lay a deep theoretical unease. Physicists understood that electric currents produced magnetic fields. They knew that magnets could induce electric currents. James Clerk Maxwell had already unified electricity and magnetism into a sweeping mathematical framework. But one deceptively simple question remained unsettled. What truly counts as an electric current? Does magnetism arise only from electricity flowing through a wire, or from the motion of electric charge itself, no matter how that motion occurs? This was not a trivial distinction. In ordinary circuits, electricity appeared as a current traveling along a conductor. The magnetic field around a wire could be measured and mapped. It seemed natural to equate magnetism with conduction current, the steady flow of charge through a material pathway. But Maxwell's theory suggested something deeper. According to his equations, magnetism was not caused by current in a wire in any special sense. It was caused by moving charge. Motion was the key. If an electric charge moves, it should generate a magnetic field. The conductor is incidental. The motion is fundamental. Yet in the 1870s, this was more of a theoretical claim than an experimentally verified fact. No one had clearly demonstrated that mere mechanical motion of electric charge, without a conventional electric circuit, could produce magnetism in a measurable way. The distinction might sound subtle, but it cut to the heart of how physicists understood nature. Was magnetism a property of circuits and materials, or a universal consequence of motion itself? The answer would reshape electromagnetic theory and reinforce Maxwell's revolutionary vision of the physical world. At that time, electricity was still commonly described in fluid-like terms. Many scientists pictured it as a kind of invisible substance that flowed through wires much like water through pipes. Magnetic fields were seen as secondary effects of this flow. The mental model was mechanical and material. To suggest that magnetism depended only on charge in motion, even if that charge was simply carried around in circles by a spinning object, required a shift in perspective. It meant that magnetism was not confined to the special case of wires and batteries. It meant that motion and charge were inseparable partners in the fabric of physical law. Henry Augustus Rowland, a physicist at Johns Hopkins University, stepped directly into this conceptual gap. He recognized that if Maxwell's theory was correct, then a charged object set into rotation should generate a magnetic field. Imagine a disk made of insulating material. If that disk were electrically charged and then spun rapidly, the charges on its surface would move in circular paths. Each tiny portion of charge would trace out a loop. From Maxwell's standpoint, that circular motion was equivalent to a current loop. And a current loop produces a magnetic field. Therefore, a rotating charged disk should act like a magnet. The idea was elegant, but turning it into a convincing experiment required extraordinary precision. The magnetic field expected from such motion would be extremely weak. The charges on the disk would be small. The speeds, though rapid by mechanical standards, would still be modest compared to the velocities of electrons in a wire. Detecting the resulting magnetic field demanded instruments of exceptional sensitivity. Moreover, The experiment had to rule out alternative explanations. Any stray currents, mechanical vibrations, or electrostatic effects could cloud the results. To appreciate the challenge Rowland faced, it helps to imagine the scientific atmosphere of the era. Experimental physics was advancing rapidly, but measurement technology was still in development. Sensitive galvanometers, devices capable of detecting tiny magnetic fields, were fragile and easily disturbed. Electrical insulation was imperfect. Mechanical systems introduced noise and instability. Rowland was not merely testing a theoretical prediction. He was attempting to isolate a subtle physical effect from a background of countless potential interferences. The conceptual stakes were high. If the experiment succeeded, it would demonstrate that magnetism arises purely from the motion of electric charge, independent of any conducting pathway. It would confirm a central insight of Maxwell's equations, that electricity and magnetism are unified through motion and changing fields. If it failed, or if the results were ambiguous, critics could argue that Maxwell's theory was incomplete, or that the relationship between motion and magnetism required revision. What made this problem so compelling was its simplicity. The apparatus could be described in a single sentence. Take a disk, charge it electrically, spin it, and measure whether it produces a magnetic field. Yet this simplicity masked profound implications. The rotating disk was not just a mechanical device. It was a philosophical test of what electricity truly is. Is it a static property that only becomes magnetically relevant when confined to wires? Or is it a dynamic entity whose motion, wherever it occurs, shapes the magnetic structure of space? At the heart of the issue lay a deeper shift in physics from thinking in terms of substances to thinking in terms of fields. Maxwell had introduced the idea that electric and magnetic phenomena are manifestations of fields permeating space. These fields do not merely describe forces between objects. They possess energy and dynamics of their own. In this view, when a charge moves, it disturbs the surrounding electromagnetic field. That disturbance propagates through space as magnetism. The conductor is irrelevant, the field is primary, but theoretical beauty is not enough in science. Physics demands evidence. The rotating disk offered a way to bring Maxwell's abstract mathematics into tangible reality. If a spinning charged disk behaved like a tiny magnet, then the connection between motion and magnetism would no longer be an assumption. It would be an observed fact. There was also a subtle symmetry involved. It was already known that changing magnetic fields can induce electric currents, a discovery made decades earlier by Faraday. This phenomenon suggested a deep reciprocity between electricity and magnetism. But reciprocity is most convincing when both directions are equally well supported. If magnetism can create electricity, then moving electricity should create magnetism, not merely in wires but universally. The rotating disk would close this conceptual loop. The intellectual courage required to pursue such an experiment should not be underestimated. Rowland was not simply confirming a routine prediction. He was venturing into territory where measurement uncertainty could easily overwhelm signal. He had to design an apparatus capable of sustaining high rotational speeds while maintaining electrical charge. He had to shield the system from environmental disturbances. He had to interpret tiny deflections in magnetic instruments and distinguish genuine effects from artifacts. Moreover, he had to confront skepticism. Scientific communities do not accept new claims lightly, especially when they involve subtle reinterpretations of well-established ideas. Many physicists were comfortable with the notion that magnetism arises from currents in conductors. Extending this idea to any moving charge required a conceptual leap. Rowland's task was not only experimental, but persuasive. The data had to be clear, repeatable, and compelling. The rotating disk thus became more than a piece of laboratory equipment. It became a stage upon which fundamental principles were tested. When set into motion, the disk carried with it the accumulated tension of decades of theoretical development. Each rotation represented a question turning in space. Does motion alone suffice to generate magnetism? To understand why this mattered so deeply, consider the broader implications. If moving charge produces magnetism, then magnetism is inseparable from motion. Every charged particle in motion, whether in a wire, in a spinning object, or even in the atoms of matter, contributes to magnetic phenomena. This perspective would later become essential in understanding the magnetic properties of materials, the behavior of electrons in atoms, and ultimately the structure of modern physics. The simple rotating disk pointed toward a universe in which electricity and magnetism are woven together at the most fundamental level. There is also an aesthetic dimension to this story. Physics often advances when simple thought experiments are made real. The rotating disk is conceptually transparent. You can picture it easily. There is no hidden complexity in its basic design. Yet from this simplicity emerges a profound test of nature's laws. Such experiments remind us that great discoveries do not always require elaborate machinery. Sometimes they require clarity of vision, the ability to see that a spinning disk can answer a question that has troubled an entire field. As Rowland prepared his experiment, he was effectively asking nature to reveal whether Maxwell's theory described reality or merely approximated it. The disk would spin, the charges would move, the magnetic detector would respond, or it would not. In that response lay the verdict. What makes this moment in physics especially powerful is that it bridges eras. It connects Faraday's intuitive experiments with Maxwell's mathematical unification. It anticipates the electron theory that would soon follow. It hints at the deeper principle, later formalized in relativity, that electricity and magnetism are different aspects of the same underlying phenomenon, dependent on motion and reference frame. Though Rowland could not foresee all these developments, his experiment contributed to the foundation upon which they were built. Before the disk ever rotated, the idea itself had already shifted the conversation. It reframed magnetism not as a property of special materials or circuits, but as a universal consequence of moving charge. It suggested that the laws of electromagnetism operate consistently across contexts. Whether charge flows through copper wire or circles on a spinning insulator, the magnetic outcome should follow the same principles. In this sense, the rotating disk represents a turning point not because it introduced a new equation, but because it tested a unifying principle. It demanded that theory and experiment align at a deeper level. It insisted that if motion and charge are truly linked to magnetism, then the connection must hold everywhere. The story of the rotating disk begins, therefore, not with spinning machinery, but with a conceptual challenge. It begins with a question about the nature of current. It begins with the recognition that motion might be more fundamental than material pathways. It begins with a physicist willing to translate abstract equations into physical reality. As the 19th century drew toward its close, physics was becoming increasingly mathematical, increasingly unified, and increasingly bold. Rowland's experiment stood at the intersection of these trends. It was precise, daring, and conceptually profound. The rotating disk was simple to describe, difficult to execute, and transformative in implication. In the quiet of the laboratory, before the apparatus was set in motion, the question hung in the air. If a charged disk spins, will it become a magnet? The answer would confirm that magnetism is not confined to wires and coils. It would show that motion itself, pure, mechanical motion of electric charge, is enough to shape the magnetic structure of space. From that realization, a new clarity would emerge. Electricity and magnetism would no longer be seen as loosely connected phenomena. They would be understood as deeply intertwined aspects of a single electromagnetic reality. And at the center of that realization, turning steadily and silently, was a disk. Henry Augustus Rowland was not born into fame, nor did he inherit a grand scientific legacy. He entered the world in 148 in Honesdale, Pennsylvania, at a time when America itself was still scientifically young. The great centers of physics were in Europe, Germany, Britain, France. The United States was known more for industry and expansion than for theoretical breakthroughs. Yet from this setting emerged a man whose quiet precision and uncompromising standards would help elevate American physics to international respect. Rowland's early life did not predict dramatic scientific revolution. What defined him from the beginning was not flamboyance, but intensity. He possessed a relentless curiosity about how things worked and an impatience with superficial explanations. While many were content to accept results as long as they seemed plausible, Rowland demanded numerical certainty. He believed that physics was not a collection of ideas, but a discipline grounded in exact measurement. For him, theory without precise experiment was incomplete. He studied at Rensselaer Polytechnic Institute, one of the few American institutions at the time with a strong engineering and scientific focus. Even as a student, Rowland showed unusual independence. He was not intimidated by established authority. If he believed a widely accepted measurement was wrong, he was willing to test it himself. That trait would define his career. He was not interested in repeating the work of others unless he could improve its accuracy. He saw physics as a craft as much as a science, a discipline requiring hands steady enough to align instruments to fractions of a millimeter and minds sharp enough to interpret subtle discrepancies. After graduating, Rowland traveled to Europe, where he encountered the rigorous standards of German experimental physics. There, he saw first, and how deeply precision was valued. European laboratories were equipped with advanced instruments, and theoretical developments were closely tied to careful experimentation. This experience shaped him profoundly. He returned to the United States determined to raise American scientific practice to that same level of excellence. When he joined the newly founded Johns Hopkins University in Baltimore, he found the ideal environment to pursue that mission. Johns Hopkins was built on the German model of research-oriented higher education. It emphasized original investigation rather than rote instruction. Rowland thrived there. He built laboratories, trained students, and cultivated a culture of meticulous measurement. He insisted that experimental error be minimized to the greatest possible extent. Sloppiness was unacceptable. Approximation without justification was intolerable. His reputation quickly grew, not as a showman, but as a master of experimental design. One of his earliest major achievements involved measuring the mechanical equivalent of heat with unprecedented accuracy. This constant, connecting mechanical work and thermal energy had already been studied by James Prescott Joule. But Rowland improved upon existing measurements, refining them to a level that impressed even European scientists. His work demonstrated that American physicists could contribute at the highest level of international science. What distinguished Rowland was not merely technical skill, but intellectual courage. He did not hesitate to challenge established figures if evidence demanded it. He once publicly criticized the British physicist Lord Kelvin for what he believed were errors in measurement. Such boldness was rare, especially for an American scientist addressing European authority. Yet Rowland was guided not by ego, but by conviction that physics must answer to data, not prestige. By the 1870s, electricity and magnetism had become central themes in physics. James Clerk Maxwell had published his revolutionary equations, unifying electric and magnetic phenomena into a single theoretical framework. Maxwell's mathematics suggested profound truths: that light itself was an electromagnetic wave, that changing electric fields could produce magnetic fields, and that moving charge was fundamental to magnetism. But theory alone was not enough. Maxwell's ideas were powerful, yet still abstract to many experimentalists. Rowland was precisely the kind of physicist needed to bridge that gap. He possessed both mathematical understanding and experimental mastery. He could grasp the implications of Maxwell's theory, while also designing apparatus capable of testing its predictions. Where some saw equations as elegant speculation, Rowland saw them as challenges to be verified. The question that drew his attention was deceptively simple: does the mere motion of electric charge produce magnetism? It sounds obvious today, but in Rowland's time, this was not fully demonstrated. Scientists knew that electric currents in wires generated magnetic fields. But whether that magnetism was due to the conductor, the structure of the circuit, or the motion of charge itself was still debated in subtle ways. Rowland understood that Maxwell's theory implied a clear answer. If magnetism arises from moving charge, then a charged object set into mechanical rotation should generate a magnetic field. No wire would be necessary, no battery, driven current, just motion. The elegance of this idea appealed deeply to Rowland's scientific temperament. It was simple in concept, yet profound in implication. Designing the experiment required more than imagination. The expected magnetic effect would be extraordinarily small. The amount of charge that could be placed on an insulating disk was limited. The rotational speeds achievable with mechanical apparatus were finite. The resulting magnetic field would be faint, so faint that ordinary instruments would miss it entirely. Rowland did not shrink from this difficulty. Instead, he approached it as a technical challenge. He refined his apparatus with painstaking care. He developed methods to measure extremely weak magnetic fields. He accounted for environmental interference. He eliminated stray currents and vibrations. His laboratory became a place where precision ruled above all else. Those who worked with him described him as intense and exacting. He demanded the highest standards from his students and assistants. Mistakes were not brushed aside, they were analyzed. Instruments were recalibrated. Procedures were repeated. He believed that nature reveals its laws only to those patient enough to listen carefully. At the same time, Rowland was not isolated from broader intellectual currents. He corresponded with leading scientists. He followed developments in Europe. He was fully aware that the success or failure of his rotating disk experiment would resonate beyond his own laboratory. It was not merely a local test. It was a statement about the validity of electromagnetic theory itself. When he finally carried out the experiment and detected the magnetic field produced by the rotating charged disk, it was a triumph not only of theory, but of character. The result validated Maxwell's insight and confirmed that magnetism arises from moving electric charge. But it also validated Rowland's philosophy of science: careful measurement, relentless refinement, and intellectual courage had paid off. His achievement strengthened the reputation of American physics at a time when it was still gaining recognition. European scientists took notice. Rowland was no longer simply a promising experimentalist from across the Atlantic. He was a contributor to the foundations of electromagnetic science. Beyond the rotating disk, Rowland made other significant contributions. He developed highly precise diffraction gratings for spectroscopy, enabling more accurate analysis of light spectra. These gratings became internationally renowned and were used by scientists around the world. Once again, his hallmark was precision. He did not settle for approximate solutions when exact ones were possible. Yet despite his accomplishments, Rowland was not driven by personal fame. He was driven by the pursuit of accuracy. His personality was serious, sometimes severe. He was not known for theatrical lectures or flamboyant public appearances. His passion expressed itself in the quiet alignment of instruments and the careful reading of scales. In many ways, Rowland embodied a transitional moment in physics. He stood between the era of individual experimenters working with relatively simple apparatus and the coming age of large-scale laboratories and institutional science. He showed that American universities could become centers of advanced research. He helped establish a tradition of rigorous experimental physics in the United States. There is something almost symbolic about the man behind the spinning disk. The experiment itself was elegant, restrained, and conceptually pure. It did not rely on grand machinery or dramatic demonstration. It relied on disciplined execution. That discipline reflected Rowland's character. He believed that nature's secrets are subtle, they do not shout, they whisper, and only precise instruments and precise minds can hear them. His life also illustrates a broader truth about scientific progress. Great advances often require individuals willing to stand at the intersection of theory and experiment. Maxwell provided the equations, but someone had to test their deeper implications. Rowland stepped into that role with determination. He did not live long enough to witness the full unfolding of electromagnetic theory into the 20th century. He died in 1901, just as physics was about to enter the revolutionary era of relativity and quantum mechanics. Yet his work formed part of the foundation upon which those revolutions were built. The confirmation that moving charge produces magnetism would later become central to Einstein's understanding of the relationship between electricity, magnetism, and reference frames. Rowland may not be as widely known as Maxwell or Einstein, but his contribution was indispensable. He demonstrated that abstract theory must meet experimental reality. He proved that American physics could stand alongside European achievements, and he showed that careful, disciplined experimentation can illuminate profound truths about nature. The rotating disk that changed physics did not spin itself. It was set in motion by a man whose mind was as precise as his instruments. Henry Augustus Rowland represents a kind of scientific heroism that is quiet but powerful. Not the heroism of grand proclamation, but the heroism of patience, rigor, and unwavering commitment to truth. In the end, his legacy is not only the magnetic field detected beside a spinning disk. It is the example he set for generations of physicists that no matter how elegant a theory may be, it must be tested with care. That measurement is the language through which nature speaks, and that courage in science sometimes means challenging assumptions with nothing more than a well-designed experiment and the confidence to trust its results. Imagine standing in a quiet 19th century laboratory. There are no digital displays, no automated sensors, no humming electronics. Instead, there is polished brass, carefully balanced shafts, insulating supports, glass enclosures, and instruments so sensitive they must be shielded from the faintest disturbance. At the center of the room sits a simple object, a circular disc mounted on an axis. It does not look revolutionary. It does not resemble the grand machines of industry. And yet, this carefully designed apparatus was built to answer one of the most subtle questions in electromagnetic theory. The core idea behind the experiment was conceptually elegant. If magnetism truly arises from moving electric charge, then a charged object placed into motion should generate a magnetic field. The challenge was transforming that idea into a physical setup capable of producing a measurable result. The design required solving three fundamental problems: how to place electric charge on a rotating object, how to spin it at sufficient speed without losing that charge, and how to detect the extremely weak magnetic field that would result. The disc itself had to be made from an insulating material. If it were conductive, the charge would immediately redistribute or leak away when rotation began. An insulator allowed electric charge to remain fixed on its surface, while the entire body rotated mechanically. Materials such as ebonite or hard rubber were suitable choices, as they could hold static charge for measurable periods. The disc had to be precisely balanced so that high-speed rotation would not introduce vibration, which could disturb sensitive measuring instruments nearby. Charging the disc required another layer of ingenuity. Static electricity generators were used to deposit electric charge onto the surface. The process had to be controlled carefully. Too little charge would produce a magnetic field too weak to detect. Too much charge might cause electrical breakdown in the surrounding air, leading to discharge sparks that would ruin the measurement. The amount of charge had to be significant but stable. Once charged, the disc was mounted on a rotational axis connected to a drive mechanism. This mechanism had to spin the disc at high speed, thousands of revolutions per minute, while maintaining electrical isolation. Any conductive pathway through the axle could allow charge to dissipate. Therefore, insulating supports and careful mechanical construction were essential. The axis had to rotate smoothly, without wobble, because even slight mechanical irregularities could create spurious magnetic effects or disturb the measuring apparatus. The logic behind spinning the disc was straightforward but profound. Electric charge distributed across the disc's surface would move in circular paths as the disc rotated. Each tiny segment of charge would trace out a loop. From the standpoint of electromagnetic theory, this circular motion is equivalent to a current loop. And current loops produce magnetic fields. In effect, the rotating disc would behave like a collection of microscopic currents arranged in concentric circles. However, there was a crucial difference between this setup and an ordinary electric current in a wire. In a wire, charges flow continuously through a conductor, driven by a battery or potential difference. In the rotating disc, the charge was static relative to the material of the disc. It was not flowing through a circuit. Instead, the entire charged surface was being physically carried around by mechanical motion. The experiment would determine whether this distinction mattered. Detecting the magnetic field posed perhaps the greatest technical challenge. The expected magnetic effect was extraordinarily weak. To measure it, a highly sensitive magnetic instrument was placed near the disc. This detector had to be capable of registering minute deflections caused by faint magnetic forces. Often, such instruments used suspended magnetic needles or mirror galvanometers, which could amplify tiny movements into visible shifts of light reflected onto a distant scale. The positioning of the detector was critical. It had to be close enough to the disk to sense the magnetic field, yet far enough to avoid mechanical interference or electrostatic attraction. Electrostatic forces from the charged disk could influence nearby objects. Therefore, shielding and careful arrangement were necessary to ensure that any observed deflection was due solely to magnetism, not electric attraction. Another important aspect of the design involved reversing conditions. To confirm that the magnetic field truly resulted from motion of charge, the experiment needed controls. If the disk was charged but not rotating, the magnetic detector should show no deflection. If the disk rotated without charge, again, there should be no magnetic effect. Only when charge and motion were combined should the magnetic field appear. This systematic approach eliminated alternative explanations. Environmental interference had to be minimized. The Earth itself has a magnetic field. Nearby metal objects could distort measurements. Even temperature changes could affect the apparatus. The experiment required careful calibration and repetition. Each trial had to be consistent. Each variable had to be isolated. When the disk was finally set into rapid rotation while carrying electric charge, the moment of truth arrived. According to electromagnetic theory, a magnetic field should form along the axis of rotation, similar in structure to the field produced by a circular current loop. The sensitive detector nearby would respond by deflecting slightly in one direction. If the direction of rotation were reversed, the direction of the magnetic field, and thus the deflection, should also reverse. This symmetry was an essential prediction. The brilliance of the design lay in its clarity. The apparatus did not rely on complex circuitry or hidden mechanisms. It directly translated theoretical prediction into physical action. Charge was placed on a disk. The disk was spun. A magnetic effect was measured. The cause and effect relationship could be traced step by step. There was also an aesthetic simplicity to the geometry. A flat circular disk, rotating about its central axis, creates a beautifully symmetric distribution of motion. Each ring of charge moves with a velocity proportional to its distance from the center. This symmetry allowed theoretical calculations to predict the strength of the magnetic field with reasonable accuracy. The experiment was not merely qualitative, it was quantitative. The measured magnetic field could be compared with the value predicted by electromagnetic theory. This comparison was crucial. If the measured effect matched the theoretical expectation, it would provide powerful confirmation that magnetism arises from moving charge, exactly as Maxwell's equations describe. If there were discrepancies, it might indicate limitations in the theory or flaws in the experimental setup. The mechanical design also required durability. High rotational speeds introduced centrifugal forces. The disk had to withstand these stresses without cracking or deforming. Any deformation could redistribute the charge unevenly, altering the magnetic field. Precision, machining, and material selection were therefore essential components of the experiment. In addition, the experiment demanded temporal control. The charge on the disk would gradually dissipate over time due to leakage through air or supports. Measurements had to be taken quickly and efficiently. The apparatus had to allow rapid charging, spinning, and detection within a controlled timeframe. One of the most elegant features of the design was its reversibility. By reversing the direction of rotation, the sign of the magnetic field should reverse. This provided a clear diagnostic tool. If the detector deflected one way for clockwise rotation and the opposite way for counter-clockwise rotation, it strongly indicated that the effect was genuinely magnetic and directly tied to motion. The rotating disk experiment was, in essence, a mechanical embodiment of an abstract equation. Maxwell's theory predicted that magnetic fields arise from electric currents, and electric currents are simply moving charges. The disk transformed that statement into a tangible demonstration. It allowed motion itself to be isolated as the critical factor. What makes the design especially remarkable is how it bridged theory and craftsmanship. It required deep understanding of electromagnetic principles, but also hands-on skill in constructing stable, precise apparatus. It was not enough to know the equations. One had to build a machine that could test them faithfully. When the magnetic detector responded as predicted, the experiment achieved more than a technical success. It provided visible, measurable evidence that motion of charge, regardless of whether it occurs in a wire, produces magnetism. The rotating disk became a powerful symbol of electromagnetic unity. In retrospect, the apparatus may appear simple, but simplicity in physics is often deceptive. Beneath the rotating disk lay layers of conceptual depth and engineering care. Each component, the insulating material, the charging method, the rotational mechanism, the magnetic detector was chosen and refined to eliminate ambiguity. The design of the experiment demonstrated a profound scientific principle. When confronting a theoretical question, strip the situation to its essentials. Remove unnecessary complications. Focus on the fundamental variables. In this case, those variables were charge and motion. By isolating them in their purest form, the rotating disk provided a decisive answer. Thus, what appeared to be a modest spinning object in a quiet laboratory became a turning point in electromagnetic science. It showed that the laws of physics are not confined to specific materials or devices. They operate universally. A charged disk in motion behaves according to the same principles as a current in a wire. Magnetism does not care about the path. It cares about the motion. The brilliance of the rotating disk experiment lies not only in its result, but in its design. It was a masterpiece of clarity, precision, and conceptual focus. Through careful construction and disciplined execution, it transformed a theoretical insight into physical reality, allowing motion itself to reveal its magnetic power. When the rotating disk finally spun under controlled conditions and the magnetic detector responded, the moment marked far more than the success of a clever experiment. It was the instant when motion itself was proven to be magnetic, not metaphorically, not theoretically, physically, measurably. The quiet deflection of a needle beside that spinning, charged disk became direct evidence that magnetism is born from moving electric charge. To understand why this was so profound, we must return to the intellectual tension of the time. Scientists already knew that electric currents in wires produce magnetic fields. This had been established decades earlier, but a current in a wire is a specific arrangement. Charges moving through a conductor, driven by a battery, constrained along a path. The deeper question was whether magnetism required that special arrangement, or whether motion alone was sufficient. The rotating disk stripped the problem down to its essentials. There was no closed electrical circuit in the traditional sense. No continuous flow of charge from one terminal to another. The electric charge was static relative to the disk's surface. It did not flow across the material. It simply sat there, but when the disk rotated, that charge moved through space. Each bit of charge described a circle. From the standpoint of motion, it was indistinguishable from a tiny circular current. And when the disk rotated, the magnetic detector deflected. That deflection was the proof. It showed that the universe does not distinguish between charge flowing in a wire and charge carried mechanically through space. Both are forms of motion, and motion of charge is what generates magnetism. This result confirmed a fundamental idea embedded within Maxwell's electromagnetic theory. Maxwell's equations had mathematically unified electricity and magnetism. They showed that changing electric fields create magnetic fields, and that moving charges produce magnetic effects. But mathematics, no matter how elegant, demands experimental confirmation. Rowland's experiment provided that confirmation in its purest form. The key insight demonstrated by the spinning disk is that magnetism is not an independent substance or force separate from electricity. Instead, it is a consequence of electricity in motion. If you freeze electric charge in place, it produces an electric field. If you set that same charge into motion, you introduce magnetism. Motion transforms electric influence into magnetic structure. The elegance of this proof lies in its symmetry. When the disk rotated clockwise, the magnetic needle deflected in one direction. When the direction of rotation was reversed, the deflection reversed as well. This mirrored behavior was exactly what electromagnetic theory predicted. It was not random, it was not accidental, it was systematic and reproducible. Moreover, when the disk was charged but not rotating, there was no magnetic deflection. And when the disk rotated without charge, again, there was no magnetic effect. Only the combination of charge and motion produced magnetism. This eliminated alternative explanations. The magnetic field was not caused by friction, vibration, or mechanical motion alone. It was specifically tied to moving electric charge. In that moment, magnetism became redefined. No longer could it be thought of merely as something produced by special materials or currents confined to wires. It was revealed as a universal property of moving charge. Every electron in motion carries with it magnetic influence. Every charged particle traveling through space generates a magnetic field around its path. This realization had enormous implications. It strengthened the view that electricity and magnetism are not separate phenomena, but two aspects of one unified electromagnetic reality. The rotating disk experiment provided a tangible demonstration of that unity. There is also a deeper philosophical dimension to this proof. The experiment subtly shifted how scientists thought about physical laws. It emphasized that laws of nature do not depend on specific devices or materials. They depend on fundamental principles. The principle here was simple. Motion of charge produces magnetism. Whether that motion occurs in copper wire, in a plasma, or on a spinning disk is irrelevant. The law applies universally. The experiment also hinted at something even more profound, something that would only be fully understood decades later. Magnetism depends on motion, and motion depends on reference frame. If you observe a charge at rest, you see only an electric field. If you observe that same charge moving relative to you, you detect both electric and magnetic effects. In other words, electricity and magnetism are intimately connected through motion and perspective. Although the full implications would later emerge in Einstein's theory of relativity, the rotating disk experiment provided early experimental support for this idea. It demonstrated that magnetism is not an independent force existing on its own. It arises from the movement of electric charge relative to an observer. From a technical standpoint, the proof required extraordinary care. The magnetic field produced by the spinning disk was extremely weak. Detecting it demanded sensitive instrumentation and repeated verification. The consistency of the results was essential. A single deflection could be dismissed as error, but systematic, reversible, predictable deflections established credibility. What made the proof so compelling was its clarity. It was not buried in complex mathematics or indirect inference. It was visible in the laboratory. The magnetic needle moved when the charged disk rotated. The universe responded to motion. This response validated a key prediction of electromagnetic theory and strengthened confidence in Maxwell's framework. It reassured physicists that the equations describing electric and magnetic fields corresponded to physical reality. It bridged the gap between abstract mathematics and observable phenomenon. The experiment also deepened understanding of current itself. A current is no longer merely thought of as something flowing in a wire. It is defined more fundamentally as moving charge. The wire is simply a convenient medium for guiding that motion, but the essence of current is motion. And magnetism arises from that motion, regardless of how it is produced. This conceptual shift would later influence the development of electron theory and atomic physics. When scientists discovered that atoms contain moving charged particles, electrons orbiting nuclei, it became clear that magnetism could arise naturally from microscopic motion. The rotating disk experiment foreshadowed this insight by demonstrating that circular motion of charge produces magnetic fields. There is also a sense in which the proof completed a circle in electromagnetic understanding. Faraday had shown that changing magnetic fields can induce electric currents. Now it was clearly demonstrated that moving electric charge generates magnetic fields. The reciprocity between electricity and magnetism became experimentally balanced. Each could give rise to the other under the right conditions. The spinning disk was not a dramatic explosion of discovery. There were no sparks flying, no loud proclamations. The proof was quiet, almost subtle, but its implications were vast. It confirmed that the electromagnetic field is governed by principles that apply universally. It strengthened the bridge between theory and experiment. It reinforced the unity of electricity and magnetism. Perhaps most importantly, it reshaped intuition. After this experiment, it became natural to think of magnetism as a dynamic phenomenon linked to motion. It prepared the scientific community to accept later developments in which electric and magnetic fields transform into one another depending on relative motion. The rotating disk proved something fundamental about nature. That motion is not merely change in position. It has physical consequences that alter the structure of fields around charged objects. Movement creates magnetism. And this relationship holds with unwavering consistency. In the broader story of physics, the experiment stands as a testament to the power of direct testing. A theoretical prediction was isolated, simplified, and examined with precision. The result confirmed a core principle that now underlies modern technology, from electric motors to particle accelerators. Every time a current flows through a circuit, every time a generator spins, every time a charged particle curves in a magnetic field, the principle demonstrated by that rotating disk is at work. The proof of magnetic motion was not just a confirmation of theory. It was a revelation about the fabric of electromagnetic reality. A disk spun, a needle moved, and in that movement, physics gained clarity. Magnetism was no longer confined to special circumstances. It was revealed as the natural companion of moving charge, a universal consequence of motion written into the laws of nature themselves. When the rotating disk experiment confirmed that moving electric charge generates a magnetic field, the immediate result was clear. But the deeper consequences unfolded gradually, sending intellectual shockwaves through the foundations of physics. What appeared to be a precise laboratory verification became a conceptual turning point. The experiment did not merely confirm a prediction, it reshaped how scientists understood electricity, magnetism, matter, and motion itself. To appreciate the magnitude of this shift, we must remember that 19th century physics was still navigating the transition from mechanical intuition to field theory. For centuries, physical explanations relied heavily on mechanical analogies, gears, fluids, tensions, and invisible substances pushing and pulling at a distance. Electricity and magnetism were often imagined as mysterious fluids flowing through conductors, or as subtle forces acting instantaneously across space. Maxwell's equations had already challenged this world. By introducing the concept of electromagnetic fields, continuous structures filling space, carrying energy and momentum. But theory alone does not instantly change intuition. Many physicists still clung to older interpretations. The rotating disk experiment struck at the heart of that resistance. By proving that mechanical motion of electric charge produces magnetism even without a conventional electric circuit, the experiment reinforced a radical idea. Magnetism is not a separate substance or force, it is a manifestation of electricity in motion. This shifted the focus away from materials and devices and toward fundamental properties of charge and motion. One immediate consequence was a strengthened acceptance of Maxwell's unified electromagnetic theory. The equations had predicted that magnetic fields arise from electric currents, and electric currents are simply moving charges. The rotating disk confirmed that the distinction between current in a wire and charge moving through space was artificial. The essential factor was motion. This alignment between theory and experiment gave Maxwell's framework greater authority and credibility. The shockwaves did not stop there. The experiment subtly altered how physicists defined electric current itself. Before this, current was often thought of operationally. Electricity flowing through a conductor. After the rotating disk demonstration, current could be defined more fundamentally as the movement of electric charge, regardless of the medium. The wire became secondary, the moving charge became primary. This conceptual shift prepared the ground for the electron theory of matter. Within a few decades, scientists would discover that atoms contain tiny charged particles, electrons, in constant motion. Once that discovery was made, the implications of the rotating disk became even clearer. If moving charge produces magnetism, then the microscopic motion of electrons inside atoms must generate magnetic effects. The magnetism of materials could now be traced back to the behavior of charged particles in motion. Thus, the spinning disk helped pave the way for understanding magnetism at the atomic level. It reinforced the idea that large-scale magnetic phenomena arise from countless tiny currents, electrons orbiting nuclei or spinning in place. The connection between macroscopic magnetism and microscopic motion became conceptually secure. There was also a broader philosophical impact. The experiment strengthened the principle that physical laws are universal and independent of specific mechanisms. It did not matter whether charge moved because of a battery, mechanical rotation, or some other cause. The resulting magnetic field followed the same rules. This universality became a hallmark of modern physics. Laws apply consistently across contexts. Another major consequence emerged in the evolving relationship between electricity and motion. If magnetism arises from moving charge, then motion itself becomes central to electromagnetic phenomena. This idea would later play a crucial role in the development of Einstein's special theory of relativity. Einstein, in 1905, showed that electricity and magnetism are deeply intertwined through relative motion. A magnetic field observed in one reference frame can appear partly as an electric field in another. In fact, magnetism can be understood as a relativistic effect of electric fields when charges are in motion relative to an observer. The rotating disk experiment, decades earlier, had already provided experimental grounding for the inseparability of motion and magnetism. While Rowland could not have foreseen relativity, his experiment reinforced the idea that magnetic phenomena depend fundamentally on motion. It demonstrated that magnetism is not an independent entity, but arises naturally from the dynamics of charge. This perspective aligned perfectly with the later relativistic interpretation of electromagnetism. The technological implications were also significant. As electromagnetic theory gained experimental support, engineers and physicists gained confidence in applying it to practical devices. Generators, motors, transformers all rely on the intimate relationship between moving charge and magnetic fields. The rotating disk experiment contributed to the intellectual assurance that the theory underlying such devices was sound. In addition, the experiment deepened the concept of symmetry in physics. When the direction of rotation was reversed, the magnetic field reversed. This mirrored behavior reinforced the principle that physical laws are sensitive to orientation and motion in predictable ways. Such symmetries would later become central in 20th century physics, guiding the development of quantum mechanics and particle theory. The ripple effects also extended into the study of electromagnetic waves. Maxwell's equations predicted that oscillating electric charges produce changing electric and magnetic fields that propagate through space as waves, light itself. The rotating disk experiment strengthened the idea that moving charge generates magnetic structure in space. This helped solidify the understanding that dynamic electromagnetic fields are real, physical entities, not mere mathematical abstractions. In a more subtle way, the experiment contributed to the gradual shift from viewing forces as instantaneous actions at a distance to seeing them as mediated by fields. The magnetic field around the spinning disk was not transmitted through contact or mechanical linkage. It existed in the space surrounding the disk. It had structure and direction. This reinforced the field concept as fundamental. The psychological impact within the scientific community should not be underestimated. When an experiment cleanly confirms a theoretical prediction, it builds confidence not only in that specific theory, but in the broader approach it represents. The success of the rotating disk strengthened trust in mathematical unification and in the idea that nature's laws could be expressed in precise equations describing fields and motion. There is also an elegance in how the experiment connected different domains of physics. It combined mechanics, the rotation of a solid object, with electrostatics, the placement of charge, and magnetism, the detection of a magnetic field. It showed that these areas are not isolated. They interact seamlessly. A mechanical action can produce an electromagnetic effect because the underlying laws are unified. This unity became a defining feature of modern physics. The more scientists explored, the more they found connections between seemingly separate phenomena. Electricity and magnetism unified into electromagnetism. Later, electromagnetism and optics unified. In the 20th century, even deeper unifications would emerge. The rotating disk experiment was part of this broader movement toward coherence and integration. In retrospect, the experiment may seem inevitable, an obvious test of electromagnetic theory, but at the time it represented intellectual boldness. It demanded that a theoretical insight be exposed to precise measurement, Its success strengthened the bridge between mathematics and physical reality. The shockwaves of this proof were not loud or dramatic. They were cumulative. They influenced textbooks, lectures, and research directions. They shaped how students learned about current and magnetism. They subtly guided future experiments. And they contributed to the growing realization that motion plays a central role in the structure of physical law. Perhaps the most profound consequence is conceptual clarity. After the rotating disk, magnetism could no longer be thought of as mysterious or separate. It was understood as a necessary consequence of moving charge. This clarity simplified the conceptual landscape of physics. It reduced confusion and replaced it with unity. In the broader arc of scientific history, some experiments open entirely new fields. Others solidify and confirm emerging frameworks. The rotating disk belongs to the latter category, but its importance is no less significant. It helped secure the foundation upon which 20th century physics would rise. A spinning disk in a quiet laboratory confirmed that motion and charge together give birth to magnetism. From that confirmation flowed deeper understanding of atomic structure, electromagnetic waves, relativity, and technological innovation. The experiment did not just answer a question, it strengthened a world. View one in which nature's forces are unified, motion is fundamental, and invisible fields shape the fabric of reality. The shockwaves continue even today. Every modern device that depends on electromagnetic interaction rests upon the principle that moving charge produces magnetism. And that principle, once a subtle theoretical claim, became undeniable through the quiet turning of a charged disk. When the rotating disk experiment confirmed that moving electric charge produces magnetism, it did more than validate Maxwell's equations. It quietly prepared the intellectual ground for one of the greatest revolutions in science, Einstein's theory of relativity. The connection may not have been obvious at the time, but the principle demonstrated by that spinning disk, magnetism arising from motion, would later become central to understanding space, time, and the nature of physical reality itself. To see the connection, we must first recognize what the experiment truly established. It showed that magnetism is not a separate force independent of electricity. Instead, magnetism is a direct consequence of electric charge in motion. If a charge is stationary, it produces only an electric field. If that same charge moves, a magnetic field appears. Motion transforms the electromagnetic situation. This relationship between motion and magnetism contains a profound hint. Magnetic effects depend on the observer's frame of reference. Imagine observing a charged particle at rest. You detect an electric field surrounding it, but no magnetic field. Now imagine moving relative to that same charge. From your perspective, the charge is in motion, and if moving charge produces magnetism, you should now detect both electric and magnetic effects. This insight lies at the heart of Einstein's 1905 breakthrough. Einstein asked a deceptively simple question: what happens to electric and magnetic fields when observed from different states of motion? Classical physics struggled with this question because it treated space and time as absolute. But electromagnetic phenomena, especially as described by Maxwell's equations, suggested something different. They implied that the speed of light is constant and that electric and magnetic fields transform into one another depending on relative motion. The rotating disk experiment had already provided experimental support for one key piece of this puzzle. Magnetism arises purely from moving charge. There is no need for special materials or unique mechanisms. Motion alone is sufficient. This meant that magnetic fields could not be fundamental in the same way electric fields were traditionally imagined. Instead, they were tied to motion, relative motion. Einstein took this idea further. He showed that magnetism can be understood as a relativistic effect of electricity. In simple terms, what appears as a magnetic field in one frame of reference can be explained as an electric field observed from a moving frame. Magnetism, in this view, is not an independent phenomenon. It emerges naturally when electric charges move relative to an observer. To illustrate this, consider a wire carrying electric current. The wire contains positive charges fixed in place and negative charges moving along its length. From the perspective of a stationary observer, the moving charges create a magnetic field around the wire. But from the perspective of an observer moving alongside the electrons, the distribution of charge appears different. Subtle changes in charge density caused by the relativistic effects of motion create electric fields that account for what another observer describes as magnetism. This interpretation would not have been convincing without experimental evidence that moving charge genuinely produces magnetic fields. The rotating disk experiment provided that evidence decades earlier. It demonstrated in clear, measurable terms that magnetism is inseparable from motion. The intellectual road from the spinning disk to relativity is not a straight line, but it is continuous. First came the unification of electricity and magnetism through Maxwell's equations. Then came experimental confirmation that motion of charge generates magnetism. Finally, Einstein reinterpreted the entire electromagnetic framework through the geometry of spacetime. In Einstein's theory, electric and magnetic fields are components of a single electromagnetic field tensor. Depending on the observer's motion, parts of this unified field appear electric or magnetic. The distinction between electricity and magnetism becomes a matter of perspective. They are different faces of the same underlying reality. The rotating disk experiment helped solidify the idea that magnetism depends fundamentally on motion. Without that foundation, the relativistic interpretation might have seemed speculative, but because motion-induced magnetism had already been demonstrated, Einstein's insights found firmer ground. There is also a symbolic continuity between the experiment and relativity. The spinning disk emphasized rotational motion and symmetry. Relativity emphasizes invariance and transformation under motion. Both challenge the notion of absolute states. In the case of the disk, magnetism appears only when there is motion. In relativity, measurements of space and time depend on relative motion. In both cases, motion reshapes physical reality. Another important connection lies in the concept of fields. The rotating disk experiment reinforced the reality of electromagnetic fields as physical entities. The magnetic field around the disk was not a mechanical effect transmitted by contact. It was a structure in space itself. Relativity would later show that space and time themselves form a dynamic structure, spaced, interwoven with fields and energy. The road from Rowland to Einstein thus represents an evolution in understanding. The experiment began with a straightforward question: does moving charge produce magnetism? The answer was yes, but that yes opened deeper questions. If magnetism depends on motion, what does that imply about observers moving relative to one another? If electric and magnetic effects change with motion, perhaps space and time themselves must adjust accordingly. By the early 20th century, these questions converged. Einstein realized that the laws of electromagnetism remain consistent only if measurements of space and time transform in specific ways between moving observers. Special relativity emerged from this realization, and within that framework, magnetism became a natural and inevitable aspect of electric phenomena viewed through motion. Thus, the spinning disk occupies a quiet but essential place in the story of modern physics. It did not announce relativity. It did not rewrite equations of space and time, but it confirmed a principle that relativity would later elevate to central importance, that motion and electromagnetism are inseparable. A charged disk rotates. A magnetic field appears. Decades later, a physicist re-examines electricity and magnetism through the lens of motion and discovers that space and time are not absolute. The thread connecting these moments is the recognition that movement changes physical reality in measurable ways. From Rowland's laboratory to Einstein's theoretical insights, the journey reveals how careful experiment can lay the groundwork for revolutionary thought. The rotating disk proved that magnetic motion is real. Relativity revealed why that motion matters so deeply. Together, they show how a simple experiment can echo across generations, shaping our understanding of the universe itself. When we look back at the rotating disk experiment today, it may seem modest in scale. There was no explosion of public attention, no dramatic unveiling before crowds. It was a carefully controlled laboratory demonstration, subtle in effect and precise in execution. Yet its legacy continues to echo through modern physics and technology. The spinning disk did more than confirm a theoretical prediction. It clarified a principle that underlies nearly every electromagnetic device in existence. At its core, the experiment established a simple and universal truth. Moving electric charge produces magnetism. That statement is now so familiar that it feels almost obvious, but before it was demonstrated with clarity, it remained partly conceptual. The rotating disk transformed that concept into measurable reality, and once proven, it became a cornerstone of how we understand electromagnetic interaction. Today, every electric motor operates on this principle. When current flows through coils of wire, magnetic fields form, interact, and generate mechanical motion. Every generator reverses that process, using motion to produce electric currents. Transformers, speakers, hard drives, MRI machines, particle accelerators, all depend on the intimate relationship between charge and motion that the rotating disk helped solidify. Beyond technology, the experiment left a permanent mark on theoretical physics. It reinforced Maxwell's electromagnetic theory at a time when field concepts were still gaining acceptance. By demonstrating that magnetism is not tied to specific materials or circuits, but arises from motion itself, the experiment strengthened the idea that electromagnetic fields are fundamental structures of nature. This clarity prepared physics for the deeper revolutions of the 20th century. When Einstein later showed that magnetism can be understood as a relativistic effect of electricity, the conceptual groundwork had already been laid. The rotating disk had proven that magnetism depends on motion. Relativity would explain how motion reshapes electric and magnetic fields depending on the observer. In this way, the experiment became part of a larger narrative, the gradual realization that nature's forces are unified and deeply interconnected. The legacy also extends into atomic and quantum physics. When scientists discovered that electrons move within atoms, the principle demonstrated by the rotating disk became essential. The magnetic properties of materials, such as ferromagnetism, arise from the motion and intrinsic properties of electrons. The idea that microscopic motion of charge generates magnetic effects traces directly back to the same principle confirmed by that spinning disk. Even in plasma physics and astrophysics, the relevance persists. charged particles streaming through space, whether in solar winds, cosmic rays, or interstellar plasma, generate magnetic fields. Planetary magnetic fields arise partly from moving charges in molten cores. On cosmic scales, magnetism shapes galaxies and influences star formation. The rotating disk experiment represents a small-scale reflection of these vast natural processes. It confirmed in the laboratory what occurs throughout the universe. There is also a deeper methodological legacy. The experiment stands as a model of how to test theory with precision. It did not rely on complicated or indirect inference. It isolated a single principle, motion of charge, and examined it under controlled conditions. It eliminated alternative explanations through careful design. This disciplined approach exemplifies how experimental physics advances knowledge, by simplifying complexity and measuring with care. In educational settings, the principle demonstrated by the rotating disk forms part of the foundational curriculum of electromagnetism. Students learn that electric currents produce magnetic fields, and that magnetic fields arise from moving charges. Though the original apparatus is rarely recreated in classrooms, its conceptual impact shapes how generations of physicists and engineers understand the subject. There is something powerful about the simplicity of the experiment: a disk, electric charge, rotation, magnetic detection. From these basic elements emerged a confirmation of one of nature's fundamental laws. It reminds us that profound truths often reveal themselves through straightforward setups when guided by clear thinking. The experiment also illustrates the unity of physics. It combined mechanics, electricity, and magnetism into a single demonstration. A mechanical rotation created an electromagnetic effect. This blending of domains foreshadowed the increasingly unified vision of physics that would dominate the 20th century. Forces once thought separate became recognized as different expressions of deeper principles. In a symbolic sense, the rotating disk represents motion at the heart of reality. It shows that movement is not merely change of position, but a generator of new physical phenomena. Motion transforms electric fields into magnetic ones. It alters the structure of space around charged objects. It creates interaction where none existed before. Modern research continues to explore this interplay between motion and electromagnetic fields. In advanced particle accelerators, beams of charged particles moving at near light speed generate complex magnetic structures. In quantum electrodynamics, the interaction between charged particles and electromagnetic fields is described with extraordinary precision. Yet at its foundation remains the same principle proven in that 19th century laboratory. The disk that once spun quietly under careful observation now stands as a historical symbol of verification. It reminds us that theoretical beauty must meet experimental confirmation. Maxwell's equations predicted the connection between motion and magnetism. The rotating disk confirmed it. That partnership between theory and experiment remains the driving force of scientific progress. Perhaps the most enduring aspect of the experiment's legacy is its demonstration of unity. Electricity and magnetism are not separate realms. They are interwoven aspects of a single electromagnetic fabric. Motion binds them together, and from that binding emerges the technological world we inhabit and the cosmic structures we observe. The spinning disk may seem small against the vastness of physics, but its impact reaches far beyond its size. It helped secure confidence in electromagnetic theory. It prepared the path toward relativity. It strengthened the field concept. It illuminated the role of motion in shaping physical law. In the end, its importance lies not in its mechanical details, but in its clarity. It answered a fundamental question with precision and simplicity. It showed that when charge moves, magnetism follows. And in doing so, it deepened humanity's understanding of the invisible forces that structure our universe.